Okay, we're now fixed it. Okay, so we're going to start with a little review of what we did in the first lecture. We talked about finite horizon deterministic dynamic programming problems, where we have states xk and control uk, and at each state xk, we choose the control, and then we move to the next state according to a given equation that's deterministic. Once we choose uk, there's no doubt which state is going to result. Moreover, there will be a cost, gk of xk and uk, that will be incurred at that stage. We accumulate those costs from the initial state to the final state xn after n stages, and we obtain an accumulated cost, which includes also a terminal cost for the final state. Now, given a control sequence, we look at this number, and it depends on the sequence and also on the initial state. And we want to find a sequence that optimizes this number. In other words, we want to find J star of X0, the minimum overall control sequences of this cost expression. And this is a function of the initial state X0. Now, to obtain this function and to obtain the optimal sequence, we use dynamic programming. And the key object here is this JK star of XK, the optimal cost of the tail subproblem that starts at state XK at time K and goes forward all the way to the end. So in the dynamic programming algorithm, we start with the terminal cost, which is the final tail subproblem by default. And then at state XK, we look at all controls, can minimize over the sum of the cost of the first stage plus the optimal cost of the following stages, which we have obtained at the previous step of the algorithm. So we go backwards from xn star, we go to xn minus 1 star for all states, then xn minus 2 star, and so on, up until we get to J0 star of X0, which is the optimal cost that we're looking for and we justify this by principle of optimality. So now once we have the J stars, we can construct an optimal control sequence by going forward. At the initial stage, the initial state, we do this calculation, obtain U0 star, the first component of the optimal sequence, then generate the new state is generated, X1 star, and we continue to go forward until we build up this entire sequence of optimal controls. Now, the problem with this is that we need to calculate this J stars before we can start with do this online play to generate the optimal control sequence. And this calculation is very difficult for a number of reasons, including the curse of dimensionality. We may have just too many states and too many calculations to do. So reinforcement learning deals with approximations, and a major approximation that we were looking at is approximation in value space. We replace these J stars that are hard to find, hard to compute, with approximations J tilde. There are many different ways we can calculate these J tildes, including offline training methods, but we're going to consider a number of different ways. And in this way, we have to do a calculation only once for every state as it is generated online. Okay, so we're now going to look at the stochastic version of this dynamic programming algorithm, stochastic problems. Then we're going to look at a class of examples, linear quadratic problems, an important class of problems which has also a very favorable special structure. and admits an analytical solution by dynamic programming as opposed to a computational solution. Then we're going to take a break and talk about infinite horizon problems and overview the theory and the algorithms for these problems. So, stochastic dynamic programming problems. They are similar to deterministic. The main difference is that a given state, xk, as you apply the control uk, the next state is random. It's affected by a random parameter wk, which we call a disturbance, and could be due to a number of different sources. So we have a system equation that involves this random parameter with given probability distribution, and we assume that it depends on xk and uk only, and it's uncorrelated to the previous disturbances, okay? The cost generated is also random, depends on wk. So the cost accumulated over n stages is a random variable. It's random because wk is random and xk is random. So we take the expectation of that and we get a number. And now here's an important difference from the deterministic case. It is important here to consider not control sequences of use, but rather policies, which are sequences of functions of the state, where each one of these components, let's say mu k at time k, is a function of xk, which comes under various names, feedback policy, or closed loop control law. There are n components of this policy, and you can view a policy as a lookup table, whereby if I give you the state at time k, you look up the table and it gives you the control. So these mu's are functions. You can view them as lookup tables. And by the way, these are functions of the state, and we assume that we know the state at time k. We're dealing with a problem of perfect state observation, where at every stage, we observe perfectly the state. Now, there is a substantive difference in using policies versus control sequences, because in a stochastic problem, if we apply a control sequence, we don't know where we're going to land, which states we're going to visit. And it is important to have knowledge of these states, to use that knowledge when choosing a control. For deterministic problems, this does not make a difference, because if I choose a control sequence at the initial state, then everything is determined. The future states are determined, so it doesn't matter whether we observe them or not, we can calculate them. But for stochastic problems, it does make a significant difference, and that's why we resort to policies. Of course, policies are much less convenient object to deal with. They involve a lot more numbers, okay? A whole lookup table. And that's one of the big differences in stochastic problems. Okay. Given now an initial state and a policy, we can compute a number which represents the cost of that policy. It is the expected value of the accumulated costs, and it's a function of x0. And the optimal cost function is obtained by minimizing the cost function of the policies over all policies. And an optimal policy is one that attains the minimum for all initial states. Okay, so now we can extend to the dynamic programming algorithm to apply to stochastic problems. Again, the key object is this jk star of xk, the optimal cost of the tail subproblem that starts at xk. And the dynamic programming algorithm starts from this terminal cost function. And at state xk, it considers the first stage cost corresponding to various controls, adds the optimal cost to go from the next state that would end up, takes the expected value, and minimizes overall controls. So it operates on the basis of some kind of principle of optimality, that once I land to the next state, I should be using the optimal policy from then on forward, and we combine everything into this equation. So we carry this algorithm backwards, starting from this terminal cost function, go backwards to state Jn minus 1, n minus 2, and so on. And at the last step, we obtain J0 star, which is the tail subproblem that starts in the initial state. Therefore, it's the optimal cost that we're looking for. Moreover, as I go backwards in this calculation, do all these minimizations for all possible states, we obtain a minimizing control. We can piece together these minimizing controls to obtain an optimal policy. So this calculation is very difficult, very long, very intensive. It has to be done for all states and simultaneously give us the optimal cost functions of the tail subproblems and the corresponding optimal policy. But there is an alternative way to implement the optimal policy if we are given just the cost to go function, optimal cost to go functions. We can go forward with online play, so to speak. Start at the initial state, compute the first control, then observe the state that's going to result, then compute the second control, and so on. One calculation per stage. However, we need to know this J stars to be able to do that, and calculating this J star is extremely difficult for the type of problem that we're looking for. So that's where, again, we have approximation in value space, and we use, in place of the J stars, some J tildes, which are obtained in some way, perhaps by offline training, perhaps in some other way. And there is also potential approximation in other places. This expected value can be very time consuming also. We may want to approximate that. This minimization may be quite difficult. We may want to approximate that. All of these things come into the concept of approximation in value space, which is very fundamental for our subject. So here's a schematic illustration of approximation in value space. And I want you to remember this figure. We're going to see it again and again. It's a very important figure for our class. It illustrates how this online play operates at stage K online. As the system is operating, we find that we are at state xk, and then we do this calculation. We introduce the cost of the first stage, and then the cost of the future as approximated by this J tilde in place of J star. Take the expected value of that and minimize over UK. So that's what we do at every stage and state. And there are three approximations here, the three approximations, which are more or less independent of each other. One approximation is replacing J star by J tilde. So we have to find various ways of calculating J tilde. We're going to go through several of those. A second approximation is in the expected value, which may be very time consuming to do exactly online. And the third minimization is third approximation is to simplify this minimization so that, again, it can be done online. And there are several variants of this approximation in value space scheme. Here, we look ahead one step and then take the approximation of the remainder through this J tilde. But we could look forward multiple steps and then take the approximation. Like in chess, we look ahead multiple steps and then use a value network to obtain the approximation of the cost to go, the scoring function, the evaluation function. Another variation is to replace this expected value with some kind of limited simulation, some kind of, we replace WK, which is random, with a deterministic quantity, some kind of certainty equivalent. That simplifies this calculation of expected value a great deal. Simplified minimization. An example of this is multi-agent rollout, which we're going to look at we're going to look at a little bit in the next lecture. This applies to the case where you have a control that consists of multiple components. And instead of minimizing over all of them simultaneously, you minimize one at a time. Turns out that you can do that and get away with it to a great extent. And that's one possibility for simplified minimization. Okay, so a lot of our course is going to deal with how do we do this approximation, how do we do this approximation, how do we do this simplification. And a particular special case to which we're going to pay considerable attention is truncated rollout with a base policy and a terminal cost approximation. We talked about truncated rollout in the context of computer backgammon and AlphaGo in the last lecture. Here is a schematic illustration. We have one step or perhaps multi-step look-ahead minimization in this box here. And then from the possible states where we land, we have a base policy, some default policy that we run forward to accumulate an approximation to the optimal cost to go. And then we take for the future a terminal cost approximation. Now, this can be viewed as a special case of that. How so? Well, the J tilde is this entire thing here. The last two steps, the rollout and the terminal cost approximation, plays the role of J tilde. Also, in this figure, it is possible that this box does not exist. We run with a base policy all the way to the end. It is also possible that this rollout is skipped altogether. We go straight to the cost approximation. And then we obtain the vanilla version of approximation in value space. So these two are very connected, almost equivalent, you might say. And we're going to talk about various ways of doing these approximations, also in the context of this rollout scheme here. Okay, now let me say a few things about Q factors. You may have heard of Q factors or Q learning. It's an important concept in approximate dynamic programming. The optimal Q factor at stage K at a given state and control pair is this expression here. It is the quantity that's minimized in the right-hand side of the dynamic programming equation, okay? That's what we minimize over U to obtain the typical dynamic programming step. Okay, so this is the definition, and the optimal Q factors are related to the optimal cost to go, the J stars. Now, notice that the dynamic programming algorithm can be written compactly in terms of Q factors like so, right? The dynamic programming algorithm is the minimum over UK of this expression. So by definition, we have this alternative expression for the dynamic programming algorithm. Moreover, an optimal policy can be obtained by minimizing this Q factor over U. So Q factors are related to our central concepts in dynamic programming. Moreover, the dynamic programming algorithm itself can be written in terms of Q factors. Okay, so here's the definition of the optimal Q factor. If I plug in this expression for jk plus 1 star, then I obtain this algorithm here. So this is an equivalent form of the dynamic programming algorithm written in terms of Q factors. Of course, it involves more storage, okay? There's a lookup table that we generate for every state control pair. There's a Q factor. We can also consider, instead of the optimal Q factors, approximately optimal Q factors, Q tildes in place of Q stars. And in this way, we will obtain suboptimal, approximate cost to go functions by this minimization, and also suboptimal policies like that. So this opens the possibility of computing approximate Q factors and doing the minimization here in an easier way, okay? Rather than minimize this expression, which involves expectation, so on, minimize this expression. And there are many different ways of computing Q factors, including neural network training by using the definition. We'll see some of those in the future. And there are several different methods. So we have Q tildes as a possibility to approximate and J tildes as another possibility. Which one of the two should we use? Well, there is an important trade-off here, a trade-off between simpler minimization and online replanning. Using Q factors allows us to simplify the minimization online by means of this expression. It is easier to minimize this expression rather than to minimize this expression, which involves an expectation here that may bother us very much. On the other hand, if we use Q factors, we're sort of stuck with this algorithm here, and we forgo the possibility for online replanning. Now, what's online replanning? It relates to a situation where the data of the problem parameters, like the system parameters, the cost parameters, and so on, change over time. And this can happen very often in the context of adaptive control situations. It is very easy to come up with problems, important problems, where you don't really know exactly the parameters of the model, or they may change over time. Now, using Q tildes allows us to do online replanning, because in minimizing the corresponding expression, we can add the new data of the problem as they change. So this is the basic trade-off between the two. They're both useful, and depending on what is important for you, you may choose one or the other. Okay, so we gave the dynamic programming algorithm, and now we're going to apply it in the context of linear quadratic problems. Are there any questions? Speak up. We have plenty of time.
Professor, I have a question, sorry.
Okay.
Are the terms, I guess I'm trying to understand the exact definition of rollout. I must have missed it, but is it similar to policy iteration? Are those two terms synonymous? Or can you explain what you mean by rollout one more time if you've already explained it?
Okay, we have talked only briefly about policy iteration, and it's a concept that applies primarily for infinite variation problems. And we're going to talk a little bit about policy iteration later in this lecture. However, rollout is simply the very first iteration of the policy iteration algorithm. Just a single policy iteration, the very first.
Okay.
Policy iteration, you generate a sequence of policies. Starting from some policy, you generate a new policy, and then a new policy, and so on. Mm-hmm. Rollout refers to the very first step of this, the very first policy that you generate from a base policy.
Got it. Okay, thank you.
Okay, so this is an example of a linear quadratic problem involving this system equation. It is a linear system equation. The control and the state enter linearly in the right-hand side, and there is also an additive disturbance here. There is no constraint on the control. And also, WK has zero mean in this example and some variance. And okay, you can view this as a model of an oversimplified cruise control system where you want to regulate the velocity of a car. You may want to, okay, the nominal velocity set by the driver, but in a more practical version of cruise control, or at least a version that's being marketed these days by car manufacturers, you may also to keep a safe distance from cars ahead, and you may use radar to measure the distance and so on. For this example, we're going to ignore these possibilities. And if we view as Vk the vehicle velocity at time k, and V bar the desired velocity, then xk represents the deviation, the error from the nominal velocity. We also assume that B is given. In practice, B can change very much because it depends on whether the road is upslope or downslope, how many passengers are in the car, a number of things that is very hard to model. But let's forget about the connection to real cruise control and focus on this system equation. And a cost, we'll assume that's quadratic. In the quadratic cost, we want to keep this xk, the error from the nominal, keep it small, near zero, and also not expand too much control. So there's a cost on the quadratic cost on the control, and it's weighted by a coefficient r, a positive coefficient r. Now, the dynamic algorithm for dynamic programming algorithm problem starts from the terminal cost, xn star, xn squared. And then at time k, at state xk, we minimize the first stage cost plus the optimal cost to go from the next state, okay? This is the next state. So this is the algorithm, and it turns out that because the system is linear and the cost function is quadratic, the algorithm can be carried out in closed form, and it yields the optimal cost to go as, I'm sorry, there's a typo here, unfortunate typo. This should be xk of xk squared, okay? Okay, I accidentally put a plus sign in instead of an underscore, okay? The optimal cost to go is quadratic. That's what we're going to show. And the kk is some scalar that can be explicitly computed. The optimal policy is a linear function of the current state. Lk, this coefficient, is a scalar that again can be explicitly computed. So it's a very nice closed form solution, a particularly nice form of policy. And moreover, the solution does not depend at all on the distribution of the disturbances, as long as it has zero mean. It depends only on the mean, which is zero. This is called certainty equivalence. The result remains unchanged if you replace an uncertain quantity by its mean. And this is a common approximation idea. It's exact for linear quadratic problems, and it's used as an approximation in other problems. So let's derive this result. Okay, so we have the first step of the dynamic programming algorithm at time n-1. That's what we minimize. This is the system function, and Jn star is a quadratic, right? So we can write this as so. And now I expand this quadratic. Is the square of this term. there's a square of wn minus 1, and there's a cross term. And then I take also the expectation inside. So that's what I get. I get the expected value of wn minus 1 here, which is 0. So this term here scratches out. And the expected value of the square, the second moment, which is sigma squared. So this step can be simplified to read like so. And the nice thing has happened. The minimization over un minus 1 is quadratic in un minus 1 and can be done in closed form. How do we do that? We set the derivative of this expression with respect to un minus 1 to 0. So that's the derivative. We set it to 0, and we solve for un minus 1.
Can I ask a question, please?
Yes, please.
So the expectation, is it kind of an operator or is it approximation function? The expectation.
No, there's no approximation in this calculation. Everything is exact. The expected value is with respect to the distribution of wn minus 1, but in this calculation, only the mean and the variance matter.
Thank you.
Does this answer your question?
Sort of. My question is the concept of the expectation in general. I didn't get the concept of the expectation.
Okay.
The context of this course.
Okay. Okay. This course requires, as a prerequisite, a first course in probability. Okay. And expected value of a random variable is what we mean in probability as expected value of a random variable. You have a random variable with a given distribution. The expected value is in that sense, in the probabilistic sense.
Thank you.
Among other things, expectation has a linearity property. Okay, expected value of a sum of variables is equal to the sum of the expected values, and that's what we have done here. We use this linearity property.
Thank you very much.
Okay. So by setting the derivative to 0, we obtain the optimal policy at the last stage. It is linear, as you can see from here, linear in the state. And we can write it like so, with ln minus 1 being the negative of this fraction here. By taking now this optimal policy and plugging it in here, we can obtain the expression for jn minus 1 star, the optimal cost to go. And because this is linear function of the state, okay, when you plug it in this expression here, for example, it becomes a quadratic in xn minus 1 plus a constant. Here's a constant and here's a quadratic, and it involves this expression here, Pn minus the scalar Pn minus 1, which is given by this. This is a calculation that is given in your text and in your class notes, and you can verify it very easily. Generally speaking, I'm going to skip some of these algebraic calculations in this example. So we started with quadratic, optimal cost to go. We ended up with quadratic again, plus an inconsequential constant. And we can go backwards in the same way.
Excuse me.
Yes.
I have a question. Is there another typo in the derivative equation? I think it should be 2, not 2b. Right? In the middle equation, 0 equals 2.
This equation here?
Yeah.
Okay.
Yeah, I thought it should be 2, not 2b.
Should be 2, not 2b.
Yeah.
Okay, I'm taking the derivative. No, you're wrong. we're taking the derivative of this expression, okay, with respect to un minus 1. So it's the derivative of the inside times the derivative of the outside. It's b times xn minus 1 plus this parenthesis. Taking the derivative of this, you use the chain rule of a composite function, and this works like you take the derivative of the inside, which is b, times the derivative of the outside. This is a quadratic, which is 2 times this parenthesis. So I think it's correct here. Okay. Okay.
Okay. Sorry.
Okay.
Yeah.
So we go backwards in the same way because the essential elements of this calculation are maintained. The cost is quadratic, and then plugging in during the same calculation gives and going backwards for all k, we obtain the optimal cost function to be a quadratic plus a constant. This is a constant. And these pKs are scalars that are generated recursively going backwards by this formula. Now, I can't explain this formula. It's just what comes out from this calculation. Moreover, the optimal policy is linear with the coefficient Lk given by this formula here. So we compute backwards these p's, and this gives us the cost, and also this gives us the Lk's, and therefore the optimal policy. It's a closed form expression, which I have abbreviated here, and part of, and you need to verify this on your own. There will be a homework also where you will practice with calculations like this. Okay, so
Professor, I
yes.
wanted to ask a question. So I see that the cost function here is quadratic. So is there any requirement like that the cost function should always be quadratic?
No, the cost function can be very general. It can be anything. This is just an example, a very favorable example.
Okay.
Okay, so let's look at linear quadratic problems in general. Again, we achieve a linear system and a quadratic cost function. We're not going to cover them. However, I want to alert you to some of the nice properties that they have. The first observation here is that the solution does not depend on the distribution of WK, only on the mean. So we can replace the random quantity WK for the purpose of calculations and the purpose of control by its mean. This is called certainty equivalence. It is correct in the context of linear quadratic problems. It is used as an approximation in the context in more general contexts. The second observation here is that this quadratic cost being maintained in backwards calculation of the dynamic programming type carries through for multidimensional problems. In multidimensional problems, instead of having a scalar state, you have a vector state. Like, for example, in two-dimensional motions, the state vector may consist of the two positions along the two coordinates and two velocities. So it's a four-dimensional vector. Here it was a one-dimensional scalar. In such a problem, it might be four-dimensional. Three-dimensional motion might be a six-dimensional vector. And the system also should be linear in this multidimensional problem. So it involves, rather than scalar B, it involves a matrix B. And there may be also some matrix multiplying the state X, but it has to be linear, multidimensional linear. The solution method extends to the case where the disturbances do not have zero mean, but have a given mean. Again, certainty equivalence holds. You can replace the disturbances by their mean and do the calculation as if the problem were deterministic. Then there is a major generalization, a fundamental result in control theory, where in our problem, the state is not observed exactly, but that is observed partially through linear measurements. For example, in two-dimensional motion, you may observe the position of some vehicle, but not velocity. So, and you may observe the position with some error using radar, but the radar has some error. Then the optimal policy can be derived in closed form again, and it involves an extended form of certainty equivalence. It has this form here. Lk is the same coefficient that we calculated for perfect state information, multiplying, instead of the state, its expected value using the measurements. So this is this expected value is provided by an estimator. Kalman filter is one possibility. You may have heard of that. There are estimators that compute these expected values for linear systems. There's a lot of theory about all this. And the optimal policy under this perfect state observations is again of this form, and certainty equivalence again holds. Okay, linear systems and quadratic costs are very basic in control theory, and they arise in many different contexts. However, some of the other assumptions that we have used here may not hold. So for example, they may be state constraints or safety constraints. Like in a cruise control context, the car has to stay inside the road and also should not bump into cars that are ahead. So in practice, such constraints can be very important, and model predictive control methodology is designed so that it's motivated by this state constraints. There may be also be control constraints, like, okay, your car cannot accelerate beyond a certain limit. And again, model predictive control takes into account this type of constraints, but still uses elements of linear quadratic theory. Finally, there are problems where some of the system parameters change, like the B parameter, and there may be other parameters there may be other parameters in the system or the cost function or the constraints. And again, we can take advantage a little bit of the linear quadratic structure, but a lot more is needed to be able to design intelligent control systems within this context. And this is the subject of adaptive control. We're going to get into this subject some more as we proceed. Okay, are there any questions?
I have a question. Could you go back to slide 9? I just want to get a clear view of what the trade-off is between the approximate QK and the JK. Now that you've finished that section, wouldn't you have to do the computation either ways in online replanning for JK as well? Yeah,
well, okay, let's consider online replanning, which arises when there are changes in this cost function and also in this system function, okay? Mm-hmm. Then using Q factors has you stuck, because this expression here does not reflect the changes in the parameters. On the other, if this is given by a neural network, the neural network has been trained already with a nominal set of parameters. It doesn't know anything about the new parameters.
Okay, yeah, now it makes sense.
Whereas here, if you know J tilde, okay, then when you calculate these expressions, you take into account the new givens, the new parameters, and you can do online replanning.
Okay. Yeah, it makes sense now. Thank you.
Okay, very good. Okay, so we did this linear quadratic problems as an example of stochastic dynamic programming. And now we're going to go into infinite horizon, which is a major subject. We're not going to cover it in detail because we're going to get into it in much more detail in towards the last 40% of the class. However, I want to give you an overview of the theory and the algorithms with a view to give you a more comprehensive view of the field, and also to make the argument that a lot of the methodology for infinite horizon problems is a straightforward extension of the methodology for finite horizon problems. Well, perhaps mathematically not so straightforward, but conceptually. So that's what I'm going to do for the rest of the lecture. But I want to take a break now and let's convene in 15 minutes. Okay, so we're back again. We finished with our presentation of the finite horizon dynamic programming. We're going to be spending a lot of time on finite horizon problems in the next few lectures. But for the moment, I want to give an overview of the theory and the algorithms of infinite horizon problems. So, okay. So this is like the finite horizon problem, but there are two differences. One is that the number of stages is infinite. We keep on controlling a system for an infinite number of stages. The second thing is that we don't allow the system function to change from one stage to the next. So the system is stationary, and similarly, the cost is stationary, except that it involves this alpha to the k, where alpha is called the discount factor. Now I'll explain what that means. So we have an infinite number of stages, a stationary system and cost, and the system is given in this form, but without the dependence of f on k. And there are states, controls, and disturbances. Disturbance has a given probability distribution that depends on xk and uk. We use policies, which have to obey a certain constraint that again does not depend on the stage, it's stationary. And the cost of the stage involves this parameter alpha here, which is called the discount factor. The cost of a policy is the limit of the end stage costs. So we look at the end stage costs and we take the limit as n goes to infinity. And okay, about the discount factor. If alpha is less than 1, the problem is called discounted. You'll see these problems very often in the literature. One reason is that they arise naturally in the system model. So the role of this discount factor is that future costs count less to us than present costs if alpha is less than 1. They're geometrically diminished with this alpha to the k. And for financial problems, this makes sense. Okay, costs in the future may count to us less than the same cost in the present. There's another nice effect that another interesting effect that this discount factor provides. It keeps the costs bounded, okay? The future costs diminish towards 0, and therefore this series here has a chance to converge rather than give you an infinite cost. The optimal cost function, this is the cost of a policy, pi at the initial state x0. The cost of the optimal cost function is the minimum over all policies. Now, when alpha is equal to 1, you have to have some other mechanism to keep the cost function bounded. So typically, this mechanism is provided by a special termination state. It's a termination state that's cost-free. Once you get there, you don't incur any costs further. And also, you stay there, a cost-free and absorbing termination state. Shortest path type problems are of this kind. And the presence of this termination state keeps the cost bounded. And essentially, the objective is to reach the termination state at minimum expected cost. So we're going to look at problems like that in the next lecture in the context of finite horizon mostly, and also in the future. But the presence of this discount factor affects the analysis quite a bit, and we will see in what ways. Okay, so this is like finite horizon, except an infinite number of steps, basically. And we would expect that dynamic programming ideas passing from finite horizon to an infinite horizon would be possible. Indeed, there are three types of theorems that are fundamental in infinite horizon problems. These are the theorems that you expect to hold, but a mathematician may not be sure actually, and may have to verify for a particular type of problem, because there are exceptions. And here are the three types of theorems. The first is that the finite horizon optimal costs converge to the infinite horizon optimal cost. Okay, the infinite horizon cost of a policy is the limit of the finite horizon cost of the policy. So is this true also for the optimal costs? Well, it makes sense, and this is the essence of this type of theorem. So let's look at this a little closer. Let's consider the n stages problem with terminal cost 0 and write the dynamic programming algorithm for it. It's given like so, okay? So n stages, we'll use the letter V to denote the optimal cost to go for this problem. V sub n is 0, and k stages from the end, the optimal cost to go is given by the dynamic programming algorithm. This is the cost of the stage, which has a discount factor, as we have assumed. So this is the dynamic programming algorithm for the finite horizon problem. Now, we divide with alpha to the n minus k, and we reverse the time index. So instead of going from n backwards, we go from 0 forwards, okay? So we redefine and introduce this function jk of x. And then after you plug into this dynamic programming algorithm, we obtain an equivalent form in terms of the functions jk. But this algorithm goes forward now, not backwards, it goes forward from 0 to 1 to 2 and so on. And because of the way the jk's have been constructed, jn after n iterations after n iterations, we obtain v0 of x, the cost of the initial state for n stages. So more generally, every time you crank this iteration here, it gives you the optimal cost function of a problem that's one stage longer, okay? jk of x is the k stages optimal cost starting from x. And intuitively, you would expect that the optimal cost is the limit of the k stages optimal cost for all states. And it can be obtained in the limit by this algorithm, which is known as value iteration. It's one of the most fundamental algorithms in dynamic programming. It's really the infinite horizon version of the finite of the finite horizon dynamic programming that we have looked at. Now you see I have some question marks here because while this theorem holds, in most cases there are exceptions. Now for the problems that we are going to be looking at, there will be no exceptions except minor exceptions, let's say. And I'm going to alert you to those. But in general, we can assume that this convergence holds. Okay. Now,
Are you going to provide an example of one of those exceptions that you spoke about in this lecture or later? Or could you provide an example right now or where it doesn't hold?
I will give an example later in this lecture in a few minutes. However, this example is going to be kind of narrow, but it will indicate what kind of things may happen. There are examples in the literature, and you can research it further. Okay. This takes us, situations where this does not hold, takes us to advanced versions of the theory of infinite horizon. But as a mathematician, it's my obligation to alert you that this is not a fact that holds universally.
All right, thank you.
Okay, so let's assume that this is true. Then we can take the limit here in this equation, in this value iteration. Limit as k goes to infinity on the left, limit as k goes to infinity on the right. And let's assume also that we can take the limit inside the minimization and the expected value. Then what we will obtain is this equation, which should be satisfied by the optimal cost function. Now, this is a very fundamental equation. The most fundamental equation in dynamic programming is called Bellman's equation. And it gives you, and it says that J star, the optimal cost, satisfies this equation. Oftentimes, it's the unique solution of this equation. Sometimes there are more solutions than just J star. And it almost always holds. You have to go into very arcane artificial examples to find a case where this does not hold. Certainly, in the problems that we are going to be considering in this course, you can take Bellman's equation as a given. However, we'll give an example a little later where there are more than one solution. So that's the second theorem. And the third theorem is an optimality condition. Suppose that you have found J star, then if you minimize in the right-hand side of this Bellman equation for every x and piece together the minimizing controls into a policy, then this policy is optimal. Notice that this policy is stationary. You apply the same control function at stage 0 as in stage 1 at any stage. The control depends only on the state where you're at, not at the stage where you're at. And again, I have some couple of question marks here because there are exceptions to this theorem. However, we will take it for granted in our analysis, and for the problems we'll look at, it does hold. Okay, so this is the basic theory, analytical theory of infinite horizon problems. And let's look at algorithms. There are two basic algorithms in infinite horizon dynamic programming. One is value iteration, which I mentioned in the previous slide. And the other one is policy iteration. Value iteration is this iteration here. It starts with J0. Now, in the previous slide, J0 is equal to 0. But in a more general version of the algorithm, the initial condition doesn't matter. As you go forward, it washes out, its effect washes out. And you start from J0, you obtain J1, J2, and so on. And the principal thing to be aware of here, to try to prove, is that JK converges to J star, okay? That's what this algorithm is used for. Calculate by iteration J star through this formula here. The second algorithm And the one that's actually more relevant from the point of view of reinforcement learning and approximations is policy iteration. Policy iteration, as you may remember, is used for offline training of the AlphaZero program. Policy iteration generates not a sequence of cost functions, but rather a sequence of policies. Starts with some policy mu0, which is arbitrary. Okay, let's say arbitrary. There's a lot of freedom in selecting it. Then generates mu1, mu2, and so on. And also in the process calculates their cost functions, or in a reinforcement learning framework, their value, their approximations to the cost functions through a value network. And the typical iteration starts with a policy and generates a new policy, and does so in two steps. One step is policy evaluation, which computes the cost function of this policy that we started with, this J mu. And now I'm giving you the algorithm in its exact form, okay? So it calculates this J mu function. This is the cost function of the policy that applies mu all the time at every stage. And then having calculated J mu, we calculate the new policy, which we will refer to as the rollout policy, using the one-step look ahead minimization that we have seen before, but except that it uses not J star, but rather J mu, the cost function of the policy that you have started with, okay? So two steps: policy evaluation, policy improvement, get a new policy, and then do policy evaluation once more, policy improvement, and so on. And this is the exact form of this algorithm. Now, a major question here is, how do you compute this J mu? How do you do this policy evaluation? There are several options. First of all, this J mu satisfies a Bellman equation. Just like we have the Bellman equation for the optimal cost function, there's a Bellman equation for J mu, which is the same thing, except that instead of minimization, it plugs in the known value of the policy, the known policy, okay? Now, this equation, viewed as having as variables the function J mu or the vector J mu in the case where you have a finite number of states. This is a linear equation, and it can be solved by any method in principle. Gaussian elimination. You go to MATLAB and you pick your favorite method for solving it, and will give you the answer. It's a linear equation. One of the ways to solve it is by using a form of value iteration, where instead of minimization, you have mu sub x in place of u here. So that's one possibility. The second possibility is to compute J mu sub x by simulation. You simply have this policy and you crank it forward for an infinite number of steps or a large number of steps, and you record the value. That gives you J mu sub x. This is Monte Carlo simulation. There's also a large class of other methods for computing J mu, both in exact policy evaluation and approximate policy evaluation. They come under the name temporal difference methods. They are considered as some of the most fundamental methods of reinforcement learning. We're not going to cover those very much because it will take us to complications that we don't want to get into, but we're going to mention them sometime later in the future when we talk about infinite horizon methods. Okay. So this is policy iteration, a concatenation of policy evaluations and policy improvements, generating a sequence of policies, and the policy evaluation is done by a number of different methods. So here's a block diagram of policy evaluation in its exact form. At the typical iteration, you start from some policy mu, the current policy, which we'll call the base policy often. And we evaluate it by any of the methods that we gave in the previous slide. And then you improve it by minimizing in Bellman's equation, but with J mu instead of J star. And that gives you another policy, which we call the rollout policy. And in exact policy iteration, you take this new policy and you make it the base policy for the next iteration, and you keep going around this loop, generating a sequence. Okay. Now, this is the exact form of policy iteration. And one thing that you can prove, with some exceptions, is that in the limit, it gives you an optimal policy. In fact, if there's a finite number of states, it will give you an optimal policy in a finite number of iterations. You don't have to go through this loop an infinite number of times. Moreover, policy iteration is faster, a lot faster than value iteration. It requires more computation per iteration, but it is a lot faster. And it's a very insightful interpretation of policy iteration as Newton's method for solving Bellman's equation. Value iteration is also an iterative method for solving Bellman's equation, but it's sort of a first order method. It's a slower method. Policy iteration is a lot faster. It's like a second order method, converges like Newton's method in just a few steps, even when it does not converge exactly. For practical purposes, after a few iterations, typically you're in, you're there. You have obtained the optimal cost function and an optimal policy. Now, going to approximations, this diagram here is for exact policy evaluation, exact policy improvement. However, you can try to do the policy evaluation inexactly with approximations using something like a value network, as in AlphaZero. You use value data, typically simulation data using the policy, and you represent the cost function of the policy by some kind of least squares fit with a neural network, and you obtain some approximator that, given a state, it gives you the value of the policy at that state. Moreover, it's also possible to implement this policy improvement by using a policy network, give you the result that gives you the result of the minimization at each state, and represent this minimization, the results of this minimization, by a network, perhaps a neural network. And in this way, you obtain an approximate rollout policy, which you plug in again as a base policy and continue. So as I said, this is what's used in AlphaZero for offline training. You do this calculation using a deep neural network, and also this calculation using a deep neural network. There's a lot of approximation involved here, but, and this is something that we're going to come back to later in the class, this method is quite resilient to approximation errors, and has a certain stability property that allows you to obtain, in the end, a policy that's approximately optimal without the approximation error blowing up with each iteration. Okay. So that's, in a nutshell, is the theory of infinite horizon problems. And of course, I have condensed it an awful lot, given you a lot of question marks. There's an awful lot of mathematics, theory, understanding that needs to be obtained, but this will serve you as a guide as to where we are going. And then we are going to be filling the gaps as we go forward. Are there any questions here?
I have a question. Is there maybe some like heuristic method of choosing intelligently an initial base policy so that you can kind of help yourself converge even faster? Or is it really just you pick an arbitrary base policy? Or yeah.
Yeah, basically you pick as a starting policy the best one you have, the best one you can.
Mhm.
There are many different ways to pick a starting policy, but they're typically problem dependent. For
Mhm.
example, you may be aware of an easier version of the problem that you have, which has an analytical solution. Then you may use the policy of that simpler problem as your starting policy for the more complicated problem.
Ah, okay. That makes sense.
Yeah, or there are other ways. There may be some preliminary calculations that you can do, some approximate calculations of a policy, and get a few data points, perhaps do some kind of least squares fit. The better starting policy you have, the better your method is likely to work. That's a general principle, but how you pick it is problem dependent.
I see. Thank you.
Okay. So now I would like to do an example, come back to this linear system and quadratic cost function, but now we introduce this discount factor here, and we take the limit of the cost as the stages goes to infinity. Now, how does the value iteration algorithm look like? It looks like this. First stage cost plus the cost from the previous iteration from the next state that we land, discounted by alpha. This is just the value iteration for this particular system equation and this particular cost function. And we take the expected value over W of this expression here, minimize over U, and this gives us a function of X. X here is a scalar, so this is a function over the real line, okay? Now, if you start with a quadratic function, this iteration, in particular, you started with 0, then with the calculations we gave earlier, you still obtain at every iteration a quadratic function. And these are, after all, the cost functions, the optimal cost functions of finite horizon problems, k+1 stages problems. And if you do the calculations, and I urge you to do the calculations actually, go through the calculations yourself, because they are instructive and they are not so difficult. We obtain the coefficients of the quadratic by this recursive formula. Okay? So the quadratic coefficient at iteration k gives you the quadratic coefficient at k+1. So this becomes an iteration which in the limit should be giving you the optimal coefficient, okay? And indeed it can be shown that the sequence of coefficients that value iteration generates converges to a limit for any non-negative initial condition. It doesn't have to be the zero, it can be also any positive number. And I'll show you a proof of that in the next slide, or a visualization of that. Now, according to the second theorem we gave, the limit of value iteration solves also is the optimal cost function, which solves Bellman's equation. Moreover, according to the third theorem we gave, and also our discussion of the finite horizon version of the problem, the optimal policy is a linear function of the state and is obtained by minimizing in Bellman's equation. Remember, the solution of Bellman's equation, J star, is K star times X squared. And that's what I have here, plus a constant, doesn't matter in this minimization. So if you do this calculation here by setting the derivative to 0 and solving, you will find that the optimal policy is a linear function of X with L being related to K star, okay? By some formula that I have not given here. Okay, so here's the visualization of what's going on with this linear quadratic problem. Remember Bellman's equation, neglecting the constant or equivalently assuming that the disturbance is 0. The Bellman equation is written like so. And if you do this minimization, then you can write this as a quadratic involving this function f. Now, f of k of the generic scalar k is given by this expression here. This comes from the previous slide, and it's a simple calculation to do this minimization of the quadratic by setting the derivative to 0. So an equivalent form of Bellman's equation is k star equals to f of k star, okay? Canceling out the x stars from both sides. In other words, k star, the quadratic coefficient of the optimal cost, is a fixed point of the function f. Moreover, the value iteration algorithm is given by this formula here, which also involves this f function. So if we cancel x star, then the value iteration algorithm is equivalent to a fixed point iteration that iterates not on functions, but rather on coefficients. Now let's try to visualize that. Let's look at this function f of k. Okay, I have drawn it here. This is the function f of k. It is concave. It approaches an asymptote as k goes to infinity. Okay, this is very easy to see from this formula. An asymptote at this value, and also it goes down along another asymptote, which you can also see here by setting the denominator to 0, basically. Goes like this. So this is the function that's involved in value iteration. And Bellman's equation has as solution the fixed point of this equation. In other words, the value of k for which this curve function meets this straight line function, which is at 45 degrees, okay? This point here satisfies k star equals f of k star, okay? And this is, in fact, the solution of Bellman's equation. Now, okay, this figure is realistic. That's how this function looks like. And there's another solution of Bellman's equation. Okay, somebody asked whether the Bellman's equation has a unique solution. There's another solution over here, which is negative. However, within the range of interest, where the quadratic cost coefficients are positive, there's a unique solution of Bellman's equation. Okay, so this is what we mean by saying that J star is a fixed point of Bellman's equation. There is a place where the right-hand side meets the left-hand side of Bellman's equation, and the point of interception is the solution. Now, how about value iteration? Okay, value iteration iterates from K0 to K1 and then to K2 and so on according to this. So at the typical step, you start out at some iterate, the kth iterate, and you have to generate the new iterate. How do you do this? Well, you go up here and then you go horizontally to this point. Then this is equal, this level is equal to f of kk, okay, this value here. And now this value, by going horizontally and going down, is kk plus 1. So the iteration starts here, goes up horizontally, and converges to k star. That's the mechanism for convergence. This staircase structure convergence. And because f of k has this nice form here, concave, you have convergence from any starting point. No matter where you start on this line, you're going to converge to this point. If you start from 0, you're going to go like this. If you start from some point above K star, then you're going to converge like this. In fact, faster. Okay? Even if you start from some negative values, you are still going to converge to K star. However, if you start from values that are to the left of this other solution, then this staircase structure is going to convert through this staircase structure. We're going to convert to K tilde. So this comes back to a question mark that I gave earlier, that the convergence of value iteration may depend on the starting point. However, the range of good starting points includes positive values, and that's all we care in this particular problem. So everything is fine. Are there any questions here? This is an important figure to understand because I can tell you lots and lots of things about value iteration and policy iteration, but a picture is worth 1,000 words. And if you understand this kind of figures, you'll get an awful lot of intuition about what's going on.
Excuse me, Professor. Is the convergence of this function is related to the convexity of the objective function? So even if we have, let's say, not convex function, do we have this convergence criteria?
Yeah, there is a relationship. If the problem has, we will going to discuss this in a couple of slides. If the problem has a finite number of states, okay, Markovian decision problems that most people, a lot of people look at, almost all the majority of literature in reinforcement learning deals with finite state problems. For finite state problems, this function or Bellman's equations right-hand side turns out to be concave, has concave components and piecewise linear.
Mm-hmm.
And that explains a lot of things, but we're going to get into this in a couple of slides.
Thank you.
Now, one more thing. How fast does this iteration converge? Well, according to this figure, it converges pretty fast, right? However, you can imagine other situations, not linear quadratic, where the corresponding figure has the right-hand side of Bellman's equation has a form that sort of is hugging. It's very close to this 45-degree line, in which case the staircase ascent towards the optimal value can be very slow. Anyway, we're going to discuss this a little later in the lecture. Okay, now let's consider again this example, the linear quadratic one-dimensional example, and look at policy iteration. In policy iteration, we start with a policy and we generate a sequence of policies. In this example, we start with a linear policy involving a coefficient L0. And if we do so, we'll generate a sequence of linear policies involving coefficients Lk that you can compute by iteration. And now I want you to look at the class notes for all the details and make sure that, that you understand the details. Our homework is also going to deal with this type of calculation. However, here I'm going to skip the details and give you the result. The policy evaluation for a given policy, mu case of x, which is a linear function of x, turns out to be quadratic plus constant. You can guess that it would be quadratic because of the type of calculation we went through in the previous slides. And the coefficient of the quadratic is given as a function of Lk by this formula here. Okay. And now, the policy improvement, this is policy evaluation. Policy improvement is obtained by plugging this into Bellman's equation and doing the minimization. And after you do that, set the derivative to 0 and so on and so forth. we obtain a new policy that's a linear function of x and relates to the quadratic coefficient of the policy cost function by this expression here. So here is policy iteration. You start with L0, calculate K0, then calculate mu1 by using this expression here, then calculate K1 by using this expression, then L2, and so on. And so this is an iteration that generates a sequence of Ks and corresponding sequence of Ls. And it turns out that this iteration is Newton's method for solving this equation here. This equation is famous. It has a name, Riccati equation. Riccati was actually a count in Italy, I think in the 1700s, which investigated a differential equation that was not linear. It was a quadratic equation, and solved it. And from his work, there's a direct line to this relation here. Riccati equations are very important in control theory. They enter in linear quadratic control. They enter in other contexts, including estimation and so on. Okay, so this is really Bellman's equation for the problem, except that it involves only the quadratic coefficient. And it turns out that policy iteration is Newton's method for solving this nonlinear equation. Now, Newton's method, you should have seen it in calculus. It involves iterations whereby at the current iterate, we linearize the equation, solve the linearized version, then relinearize at the new iterate and going forward. Newton's method has very fast convergence, has so-called quadratic convergence. And indeed, this iteration is very fast. Just a few iterations, so 5, 10, or so on, and you're in, okay? You have essentially the solution. Now, rollout, the rollout algorithm is a single Newton iteration in its exact form, the very first iteration. So it can give you a very substantial improvement in just one step in its exact form and also its approximate form. So these are the formulas for policy iteration for the linear quadratic problem. And I'm skipping the details of the calculations, but I want you very much to look into them from your class notes.
Professor, I have a question.
Yes.
Now that you've discussed the infinite horizon problem, if we go back to the stochastic version, that the finite horizon problem that you dealt before, and we take this, how different will the control signals be between that, using that as the solution, in an online system, and using the infinite horizon policy for the control signals? Like, will there be any difference in the speeds or the trajectories of the car?
Yes. Okay. The difference is that in finite horizon, the control functions, mu0, mu1, and so on, differ from one period to the next. So the control is non-stationary. As you get towards the end of the horizon, basically you're facing a different problem. You have different considerations to when you're calculating the control. Whereas for an infinite horizon problem, at any one stage, you look forward to the same problem. You look at the same infinite number of stages. So the control depends only on the state and not on the stage. There are no end effects, no end of horizon effects in finite horizon problems. That's the difference in practice.
What I mean is that if I'm an external observer and I'm looking at this adaptive control system, one which uses this finite horizon to compute the control signals on a track, and the other which has computed it, assuming that it's infinite horizon, but it's still a finite track, and the car runs on both. Will there be any noticeable difference between the quality of the car's speed or control between both?
Well, this depends on the discount factor, okay? a smaller discount factor is almost like a finite horizon problem, because after a certain point, the cost function doesn't matter anymore. It's so discounted that it doesn't matter, okay? So, but if alpha is close to 1, then there will be some difference. Okay, there are a lot of other considerations that we can discuss offline
Cool.
if you're interested in this problem.
All right, thank you.
Okay, so now I want to take you into a different landscape, a more abstract view of value iteration and policy iteration. If you're looking at insight on how these algorithms work and how the theory works, this abstract view is very helpful. It involves using Bellman operators to describe the operations of the value iteration, policy evaluation, policy improvement, and so on. It also allows a visualization of what each algorithm does. If you understand this abstract view and you're a mathematician, then you'll be able to go into the analysis in a lot more depth and with much more convenience. If you're not interested so much in the mathematics, but you'd like to get a pictorial view of what happens with the various methods, again, the abstract view is very useful. On the other hand, abstract views require abstract thinking, and oftentimes it takes some, you have to have some courses, mathematical courses, mathematical background to understand this type of abstraction properly. And what I'm going to do today is give you a bird's eye view of what's possible with abstract notation. We'll come back later to abstract notation towards the end of the course because we want to be more general. One of the benefits of abstraction is that you're able to deal with, in a unified way, with across a broad landscape of different problems. And we're going to try to do that near the end of the course as we have better understanding of the various methods. For the time being, I want you to spend, I want you to sensitize you to what's possible from a theoretical point of view and also from the point of view of visualization in this infinite horizon landscape. So if you don't understand everything or anything in the remainder of this lecture, don't despair. Go back and study a little bit, and maybe a lot of things will become clear to you, and then you'll be very happy that you looked at this type of notation and visualization. Feel free to interrupt me for questions, and hopefully I'll be able to answer them. Okay, so we introduce abstract notation and the Bellman operator. Bellman's equation is given by this expression for the discounted problem. One stage cost, optimal cost to go, appropriately discounted, minimization. There's one equation for every state. If there's a finite number of states, this J stars of X is a vector. N states, n-dimensional vector. If it's an infinite dimensional, if it's an infinite number of states, this involves a function. It's a functional equation. Now, let's consider the right-hand side, okay? This entire right-hand side, and write it as an operation that takes J star into T J star. T is the Bellman operator that transforms a function J into another function, T sub J. Again, these are functions of the state. So this is the operator. You feed it with the function J, and it does basically a dynamic programming operation, and it gives you T sub J. T sub J, the Bellman operator, is really the dynamic programming operator. Starts with a cost function, gives you another cost function. It's like a subroutine, okay? You feed it a cost function, it gives out another cost function. Now, With this notation, you can write in shorthand an awful lot of stuff that's useful and relevant to us. Value iteration is simply this fixed point iteration. Each value iterate is obtained by applying this Bellman operator or dynamic programming operator to the current iterate. Jk is the current iterate, T sub jk is the next iterate. That's value iteration. And it's very shorthand, okay? Just as there is a Bellman operator involving a minimization over controls, there is also another Bellman operator corresponding to a given policy mu. And we will denote this by T sub mu. And the corresponding Bellman's equation for J mu is this. This is what is satisfied by the cost function of a policy, as I mentioned a couple of slides earlier. And T mu sub J mu is given by this expression. Generally, T mu sub J involves putting in this equation J in place of J mu. And now we can write policy iteration in a compact form. The policy evaluation operation is this. Given mu k, we find a fixed point, a solution of this shorthand equation, a fixed point of the operator T mu of k. And policy improvement can be written like so. We find the new policy, mu k plus 1, that attains the minimum in Bellman's equation when J mu of k is used in place of J star. So policy evaluation, policy improvement, they are written in shorthand, compactly, and from the point of view of mathematical proofs and visualization, this is very useful. Moreover, I'm going to argue pictorially that the policy iteration sequence, the sequence generated by policy iteration starting from some initial policy, mu0, is the result of Newton's method for solving this Bellman equation. Okay, any questions here that might be helpful to answer? Okay, so here is a value iteration, and notice, spend some time to try to understand it, okay? I have here an illustration of the Bellman operator. It takes J and it produces T sub J. So T sub J is just this red function here, a function of J. Of course, J is multi-dimensional, so this is a projection onto a one-dimensional plane. If you have only one state, this figure would be accurate. If you have two states, then you have a figure that has a two-dimensional plane in its horizontal and a two-dimensional plane in its vertical. So you can't put it on paper. However, we will use our imagination and projection onto a one-dimensional graph. And this is the result of Bellman's operator operating on J. Now, Bellman's equation and the optimal is this, and the optimal cost is the fixed point of this T sub J. So it corresponds to the point of interception of the graph of T sub J with a 45-degree line, and it's the point where J is equal to T sub J. Left-hand side equals to right-hand side. And this red circle here corresponds to the optimal cost. So that's the point we want to find. And value iteration, remember, is given the current iterate, you apply the Bellman operator to it, and obtain a new iterator. So what does this correspond to in this figure? You start from an initial iterator J0. You calculate T sub J0, and then you try to find, and this is J1, okay? How do you construct that? You go horizontally and then go down, and this gives you J1. Now, how do you construct J2? J2 is equal to T sub J2, T sub J1, I'm sorry. T sub J1 is this level here, and you can mark it on the horizontal like so. So value iteration is just the staircase construction on this figure here. It has this form with T being the Bellman operator that maps functions J into functions T sub J. And that's not so hard to understand. I think that you're getting the drift of it. I'm sure if you remember the linear quadratic example, where value iteration was again obtained by a fixed point calculation. Basically, it's the same calculation as this figure, except for the fact that T sub J involves an x squared, a quadratic. So instead of operating on functions, we operated on coefficients of quadratics in the linear quadratic example. Okay, so that's the geometric interpretation of value iteration. And you may notice also that some characteristics of this red graph here, the right-hand side of Bellman's equation that involves this minimization of it is concave. And it's also, I've drawn here as piecewise linear. Now, this corresponds to the case where the number of states is finite and the number of controls is finite. For every control or for every given policy, this expression here is linear. We take the minimum over all controls or over all policies, and that's why we have this piecewise linear and concave structure. Basically, for every policy, there's a linear function here. A linear function, you take the minimum over all policies and you get a piecewise linear function, which is concave. This is very nice and very important for visualization. And as we will see, it explains a lot of things for policy iteration as well. So this is not just any operator. It tends to have concavity properties by nature. And particularly in the case where there is a finite number of controls, you have a piecewise linear concave structure. Now, let's go to policy iteration and try to interpret that. This is a more difficult visualization, and I hope you'll spend some time to understand it because it reveals an awful lot about policy iteration. Okay. So here is the Bellman, the right-hand side of Bellman's equation, the red curve, and the point of interception with the left-hand side, which is just J. J equals to T sub J is this point here. So the optimal cost is right here as before. Now, this is the, and in the case of, I've drawn again as concave and piecewise linear, which it is if you have a finite number of controls. Now, suppose you focus attention on a single policy and you look at Bellman's equation for that policy. Then this is a linear equation and it's this blue straight line. And J nu is given at the intersection of this blue line with a 45-degree line. It's the point where J nu is equal to T mu sub J nu. And this is the evaluation phase, the policy evaluation phase of policy iteration. Given a base policy, we find its cost and as the point of interception of these two lines or two planes in a more complicated figure. Okay, so each slope here corresponds to a different policy, and as you change the policy, this blue line changes and gives you the corresponding evaluation. Now, suppose we start with a policy, evaluate it, like I've described here. So we linearize Bellman's equation and solve the linearization, obtain this J mu. And now we go down onto the red curve and pick out the policy whose slope is the one at this point. So now the new linearized Bellman equation at J mu yields the segment, the linear segment on which we're at. So this is the slope that corresponds to the rollout policy, mu tilde. And how so? Well, policy improvement minimizes over mu this expression. So the point where this minimum is obtained at J mu is the rollout policy. That's the definition of the new policy in Bellman's equation. So we start with this policy, evaluate it, and then come down here, obtain the policy evaluation, pick out the slope of the segment where we are, linearize the equation, and that gives us the cost of the new policy. Now, this is exactly what Newton's method does. That's the interpretation of policy iteration as Newton's method. At each policy, linearize the Bellman equation that we're trying to solve and solve the linearized equation, which gives us the new policy and the new cost function. Okay, so start with the policy, evaluate it, obtain the new policy by picking out the slope, and evaluate again, and now go down here, obtain a new policy, and in this figure, policy iteration has converged in two iterations. After the second iteration, we have obtained the linearized Bellman equation is locally the same as the nonlinear Bellman equation. Okay. So how about rollout? Rollout is the first policy iteration. So you start with a base policy, evaluate it, and then roll it out, but finding the corresponding slope through policy improvement. And this is the cost function of the rollout policy. So it's very close. In one iteration, it has become very close to the optimum. That's the secret why rollout is a good algorithm. It is Newton's method, and it gives you an iterate that's pretty close to the optimum. Not always, but very often. So that's the point I'm making here. The rollout algorithm is a single iteration of the policy iteration method and also Newton's method. All of this visualization is possible because of the abstraction. Viewing, introducing the Bellman operators and putting them out in a figure, and also writing them in compact, writing the various algorithms in compact form so we can understand them better and we can work with them better. I don't expect you to understand everything here, but I want you to try to understand. And then as we go forward, you will understand better, and I'm sure you will see a benefit from that. Any questions here? Okay, we reached the end of the technical part of this lecture. In the next lecture, we're going to cover problem formulations by dynamic programming. How do we model dynamic programming problems? How do we reformulate problems that don't neatly fit into our framework? I mentioned earlier that dynamic programming is a very general methodology, but we have made a lot of assumptions in our basic model. So what I'm going to argue in the next lecture is that given just about any kind of problem, there is a way to reformulate it into our basic format and apply our algorithms through a technique which is called state augmentation. Section 1.4 of your class notes has a lot of material. And I want you to study this material before you come to class. You can see that I'm going fast, and I think there will be a benefit for you if you do some reading ahead, and both at the class notes and the slides that I'm putting online. So in particular, we're going to look at problems involving a terminal state, like shortest path type problems, where there's a state that once we reach it, we don't move from that state anymore, and we pay no more costs. There are quite a few problems of this type involving a terminal state, including the game problems, by the way, like backgammon and chess. There's a terminal state where the end game has ended, okay? So we're going to see how problems with the terminal state can be mapped into our framework. Then the system equation involves dependence on just the control UK, but in practice there may be dependencies on previous controls. There may be a delayed effect of control actions into the present state. We're going to see how we can deal with that situation. The disturbances are assumed to be uncorrelated in the sense that the probability distribution of WK depends only on XK and UK, but not on WK minus 1, WK minus 2, and so on. Correlations are common in practice, and we can deal with them by means of this technique of state augmentation. There may be problems that depend on forecasts, okay? At the beginning of each period, there may be a forecast that you may receive about the probability distribution of the disturbance. Again, we can deal with forecasts in the same way. We can deal with delays in the state system equation. Xk plus 1 may depend not only on Xk, but also on Xk minus 1, Xk minus 2, and so on. All of this is possible by state augmentation, and it's a very, very general, very powerful technique. We see that we can model anything that one can throw onto us into our format using state augmentation at the expense of more complex formulation. It doesn't come for free. Now, the biggest reformulation of all is imperfect state information. We have assumed perfect state information in our framework. The control depends on the current state, which is assumed to be perfectly known. In practice, however, we may have partial state observation. For example, in the state vector of a vehicle, a moving vehicle, in three-dimensional space is six-dimensional, 3 position coordinates and 3 velocity coordinates. The radar can measure position, doesn't measure velocity ordinarily, measures velocity indirectly. Moreover, the position measurements may be corrupted by noise. That would be a case where the state is not perfectly observed and must be quote unquote estimated using the measurements. Now, from a practical point of view, imperfect state information problems are much more difficult than in perfect state information and perfect state formation problems. Vastly more difficult. From a conceptual point of view, however, they can be reformulated into perfect state information problems by using a form of state augmentation, by passing into a different state, a so-called belief state, which is a probability distribution over the true states of the system. So there's a dynamic programming algorithm that operates on belief states, and everything that we have talked about so far, including dynamic programming, value iteration, policy iteration, approximations, rollout, and so on, all of this applies to the belief state formulation of the POM DP. Then we're going to talk about multi-agent problems where the control consists of multiple components, one component per agent. Now, these components have to be coordinated in a perfect state information of the problem, what's also called a classical information pattern. All the agents are sharing information. Information is common to all of them. And however, in practice, the agents may not share exactly the same information. So that deals to the whole general area of multi-agent problems, which face the difficulty with a non-classical, non-shared information, and also another difficulty, namely their controls consist of multiple components, which explodes the search space. When you minimize in Bellman's equation, you minimize over a much larger space in a multi-agent problem case. We are going to deal with these problems, reformulate them, and see what we can do with them. Finally, we're going to say a few things about systems with unknown or changing parameters and the whole subject of adaptive control, how you deal with changing parameters. There may be a simultaneous identification, system identification and control, or they may be an online replanning. There are various ways one can deal with adaptive control, and we're going to say a few things about them in the next lecture. We're going to cover a lot of ground, but not very deeply, just in the way of giving you the big picture of the reinforcement landscape, and then we're going to be filling in the gaps as we go forward. So I want you to read section 1.4 of the class notes, and I'm going to post homework around the linear quadratic problem. It will be announced online, and it will be due in 1 week. So that's the end of the lecture today. Are there any questions about what we did and where we're going? Okay, well, that's the end of the lecture. We can all go and watch videos of the inauguration, the presidential inauguration. At least I have. Perhaps you have watched it already. And I'll see you next week. I see something in the chat about